In this video, we will discuss the ideal antimicrobial agent, factors that affect the efficacy of antimicrobial methods, and methods for evaluating disinfectants and antiseptics. There are many antimicrobial agents available to control the growth of microorganisms. When selecting an antimicrobial agent, ideally, one would want to select one that is inexpensive, fast-acting, stable during storage, and capable of effectively controlling microbial growth, while at the same time being harmless to humans, animals, and objects on which we use them. As we will see throughout the material regarding antimicrobial agents, there is no ideal agent. Each will have its own limitations. When selecting an agent, at least 3 factors must be taken into consideration. One factor that must be considered is the site to be treated. Harsh chemicals and extreme heat cannot be used on humans, animals, and fragile objects. The type of medical procedure will also dictate which type of method is desired. Procedures that are not invasive and only make contact with mucous membranes or skin, such as auscultating heart or lung sounds, taking a patient's temperature, or blood pressure, only require disinfection of the equipment. On the other hand, equipment utilized for invasive procedures, such as needles or scalpels, require sterilization because there is a greater risk of introducing microorganisms that could cause infection. We also take into consideration the relative susceptibility of the microorganism that is to be killed. The susceptibility of microorganisms lies along a continuum from those that are most susceptible, meaning that they are easily destroyed, to those that are very resistant to antimicrobial action. We have already discussed the challenges in destroying prions. They are more resistant than any of the living microbes, and special guidelines outlined by the Centers for Disease Control and Prevention are followed when they are suspected. As previously stated, we will consider endospores the most resistant structure to be targeted by the antimicrobial methods we will explore. There are a number of medically important bacteria in the Bacillus and Clostridium genre, including Bacillus anthracis, the causative agent of anthrax, Clostridium tetani, the causative agent of tetanus, Clostridium botulinum, the causative agent of botulism, and Clostridium perfringens, the causative agent of gangrene. Endospores are resistant structures that allow the bacteria to survive harsh conditions. Bacterial endospores are very resistant to heat, radiation, and chemicals. Mycobacteria, while not as resistant as an endospore, are far more resistant than many other microbes. Their resistance is attributed to the presence of the mycolic acids within their cell walls. The mycolic acids prevent their cells from drying and protects them from many water-based chemicals. It is important for healthcare personnel to have an understanding of such resistances so that they can select the appropriate methods to kill such an organism. At this point in the semester, you should be aware that Mycobacterium tuberculosis is the causative agent of tuberculosis. With this information, it would be important to ensure that following treatment of a tuberculosis patient, that proper techniques that effectively destroy them are employed to rid the bacteria to prevent transmission to other patients. Protozoan cysts are also relatively resistant to many antimicrobial methods. Protozoan cysts are dormant structures that permit protozoans to resist harsh conditions. These structures are analogous to the endospores of bacteria. When considering the resistance of viruses, naked viruses are more resistant to antimicrobial methods than envelope viruses. This is because the phospholipid structure of the envelope is more easily disrupted than the protein capsid. While the envelope viruses do contain a nucleocapsid enclosed within the envelope, the nucleocapsid of the envelope virus is unable to attach to host cells by itself, and therefore requires the glycoprotein spikes of the envelope to attach to host cells. The effectiveness of chemical agents to inactivate or destroy microorganisms is described as high, intermediate, or low. You must have a solid grasp of these terms as you move into the lecture regarding chemical methods of control. You will be responsible for describing the level accomplished by each group of chemicals. High-level germicides are agents that kill all pathogens, including endospores. Therefore, high-level germicides can also be referred to as sterilants. Such chemical agents can be utilized to sterilize medical equipment that is sensitive to heat, such as catheters and implants. Intermediate-level germicides can kill fungal spores, protozoan cysts, and pathogenic bacteria, but are unable to destroy endospores. They are used to disinfect non-invasive instruments that come into contact with the mucous membranes of patients, such as respiratory equipment and thermometers. Low-level germicides are only effective against vegetative bacteria, fungi, protozoa, and envelope viruses. Such agents are used to disinfect electrodes, straps, and furniture that come into contact with the patient's skin. Finally, antimicrobials can be affected by environmental conditions. The temperature at which an antimicrobial agent is applied is important. Generally, a higher temperature causes the agent to be more active, because chemicals react faster at higher temperatures. pH is also important for some antimicrobials. In some cases, an acidic pH allows the chemical agent to be more effective. A very important environmental factor that must be considered is whether or not organic materials are present. Organic materials include items such as blood, vomit, urine, fecal material, other bodily secretions, and biofilms. Organic materials can interfere with the effectiveness of the antimicrobial agent. Some chemical antimicrobials are actually inactivated in the presence of such materials. Objects that contain such material should be cleaned to physically remove the organic material before they are sterilized or disinfected. Several methods have been developed that serve to measure the efficacy of antimicrobial agents. The first of the methods is the phenol coefficient. The phenol coefficient method was developed in 1903. This technique compares a disinfectant or antiseptic with phenol under standard conditions. A phenol coefficient greater than 1 suggests that the disinfectant or antiseptic is stronger than phenol, while a phenol coefficient less than 1 indicated that it is weaker. Many of the antimicrobials used today are much more effective than phenol, and thus have phenol coefficients greater than 1. The larger the coefficient, the more effective the chemical is in comparison to phenol. Your textbook gives the example of chloramine, which is a combination of chlorine and ammonia. Chloramine has a phenol coefficient of 133 when it is used against Staphylococcus aureus. This means that it is 133 times more effective than phenol. This method has been replaced by newer techniques. Currently, the United States has been utilizing a method known as the use dilution test. This test assesses the efficacy under standardized conditions using a specific set of bacteria. Metal cylinders are exposed to broth cultures containing the bacteria. The metal cylinders are then exposed to different dilutions of a particular disinfectant for 10 minutes. Following exposure to the disinfectant, the cylinders are rinsed with water to remove the antimicrobial chemical, and then the cylinders are placed in fresh media to monitor for growth. The most effective agent is the one that is able to prevent microbial growth at the highest dilution. The more dilute a chemical is, the more likely it is to be safe for humans, animals, and objects on which we intend to use these antimicrobial chemicals. However, we want to be sure we have completely eliminated the microorganism. There are some concerns regarding this technique, including concerns regarding its accuracy, so scientists are currently working to develop a new standard. The Kelsey-Sykes capacity test is the current standard approved by the European Union. We will not delve into the details of this particular method. The last method, known as the in-use test, is probably the most accurate of these techniques in regards to determining which disinfectant or antiseptic should be used in a real scenario. The in-use test requires that swabs be taken from objects before and after the disinfectant or antiseptic is employed. The swabs are inoculated on media, and then growth is examined following incubation to determine the efficacy of the agent used. Again, this method is not set against standardized conditions, but rather allows for an accurate assessment of the effectiveness of an antimicrobial agent in a specific situation.